So what I want to do now is I want to talk about what's called the binomial theorem, which is one of the, this is one of the big insights that Newton gave to us. Sometimes it's called Newton's binomial theorem. And actually there's kind of the classic binomial theorem, which was known, it's been known for a long time. So something, it's known to the ancient Babylonians, it's been known for a long time. And the classic binomial theorem says that if n is a positive integer, or even a non-negative integer, then we have a formula for the sum 1 plus x to the n. And that formula is going to be 1 plus nx plus n times n minus 1 over 2, x squared, and so on, all the way out to x to the n. And here the and so on means this is really going to be the sum as k goes from 0 to n of n choose k times x to the k, where n choose k is n times n minus 1 all the way down. You have k terms, so that means that you stop at n minus k plus 1. Yeah, so and then you divide by k factorial. So that's what this formula is. These are called binomial coefficients. So for example, if you were to look at 5 choose 3, this would be, you would have 5 times 4 times 3, and you would stop when you get to 5 minus 3 plus 1. So that would be 3. So you got 5 times 4 times 3. So here n minus k plus 1 is 5 minus 3 plus 1. So that's 2 plus 1 or 3. So that's going to be the last term that you have. Then we're going to divide by 3 factorial. And so it turns out that this is going to be, let's see, 3 factorial is 3 times 2 times 1. So the 3's will cancel. And then 4 over 2 is going to be 2. And then 5 times 2 will be 10. Okay, and so 5 choose 3 is 10. So that's what these binomial coefficients are. Now it turns out what these binomial coefficients really are is the values in Pascal's triangle. Right, so what you do in Pascal's triangle is you add up the 2 entries above it. So you get 1s along the diagonal, you add up the values above it. Everything is super nice. And here we just found 5 choose 3, so you have to go in the 5th row of Pascal's triangle. We start at the 0th row. So this is the 0th row, and then row 1, 2, 3, 4, 5. We look at the 0, 1, 2, 3rd term, and that's 10. So that's why 5 choose 3 is equal to 10. This is the 10 that we found there. And of course, there's nice symmetry. There's so much we could say about the binomial theorem and binomial coefficients. But what I'm going to do is actually argue that, one of the things that Newton did is he actually showed that you can extend the binomial theorem not just to complex numbers, but also to non-negative, to non-integers, right? Alpha can really be anything that we want as long as it's, let's just for now say that alpha is, we'll see what restrictions we have on it. There's no need to actually restrict us ahead of time. Let's just see how this goes. And so let's call this our f of z. Notice that since we're taking a power, since we're looking at alpha as being a power, we have to talk about, if alpha was a positive integer, then we wouldn't have to worry about anything. But since alpha is not a positive integer, then we have to talk about the principal branch. So let's just assume that we're working on the principal branch. Okay, so as soon as we talk about exponents, we need to go back and deal with that annoying principal branch. And then let's think about what the power series is going to be. And so if we look at f of z, let's just think about what all these values are going to be. And let's just expand. We can expand really along any value that you like. Let's expand along z equals 0. So let's take our z naught to be 0. And so what I want to do is I want to take the derivative, and I want to think about what all these derivatives are at 0. And so f of 0 is just 1 to the alpha, which is 1. And f prime of 0 is going to be alpha times 1 plus z to the alpha minus 1, which is going to be, so this is restricted to z equals 0, and that's going to be alpha. And I want to do just a few of these to get the pattern here. The second derivative is going to be alpha times alpha minus 1 times 1 plus z to the alpha minus 2. And then we're going to restrict to z equals 0. So that's going to give us alpha times alpha minus 1. And what else do we do? So then the third derivative evaluated at 0 is going to be alpha times alpha minus 1 times alpha minus 2. And that's what the derivatives are going to be. And this looks a lot like what we had up here, where you have this n times n minus 1 times n minus 2 times n minus 3. Here we have alpha times alpha minus 1 times alpha minus 2. And so here what we're going to do is we're going to define alpha choose k, where alpha is a complex number and k is a integer greater than or equal to 0. And this is going to be defined the same way. This is going to be alpha times alpha minus 1 all the way down to alpha minus k plus 1 all over k factorial. Okay, and so alpha choose 0 is just 1. So for example, alpha choose 2 is going to be alpha times alpha minus 1 over 2 factorial. So that's alpha times alpha minus 1 over 2. Alpha choose 0 is just going to be 1 just by definition, so I have to add that in actually. That doesn't follow immediately from the formula. So this is the formula if k is greater than 0 and alpha anything choose 0 is 1. Now, we have to be a little bit careful here. When you have a positive integer for your alpha, so alpha in general is allowed to be any complex number, but notice that when you have a positive integer, what's going to happen is, so if you have like 1 plus z cubed, eventually when you take enough derivatives, you're going to eventually be multiplying by 0, because your n minus 4, for example, will be 0. So if you, I'm not saying anything groundbreaking, if you take a cubic polynomial and you differentiate 4 times, you get 0, which we know. But if alpha is not an integer, then this behavior doesn't happen. And so what's happening here is that these derivatives, so the kth derivative of our function f, remember f was 1 plus z to the alpha, our kth derivative at 0 is going to be, so it's just the numerator here, but it's going to be alpha choose k times k factorial. And therefore, this function is going to have a power series representation as k goes from 0 to infinity. We're going to have the kth derivative of f at 0. So that's alpha choose k times k factorial divided by k factorial. So remember that if I take this k factorial and move it over, this gives us our coefficient c sub k. So it turns out that those are the only things that remain, times z minus 0 to the k. And so this is our formula here. And this you can check is going to be valid if z is on the unit disk. Okay, so I'll leave that to you to check that this is valid if z is on the unit disk. Okay, not much changes if you expand along, instead of expanding along 0, if you have a different center of the power series. Okay, so not too much is different, but I'll leave the details there to you. Okay, so this is the complex binomial theorem. So what this says in a nutshell, let me just write it out, is that if you look at 1 plus z to the alpha, and in particular, you look at the principal branch, okay, which we need in order to make this well-defined, then this is going to have a power series representation of k, this is the sum as k goes from 0 to infinity, of alpha choose k, z to the k. In other words, this is 1 plus alpha z plus alpha times alpha minus 1 over 2 z squared, and so on. Okay, and it's going to be an infinite sum, and it turns out that even this is valid where alpha is a complex number, z is a complex number, and everything is still good. Okay, so this is again called the complex binomial theorem, or Newton's binomial theorem. Okay, so here's another example of a power series.